so that's a number of applications. So now let me get to the application, for example, of crowd counting. I want to count like how many people are walking around. And you see. So here's what we've done. So one possibility is like you go and sort of count everybody, and that's fine. What we're doing here is, I guess, do something much simpler. We already have this segmentation, okay, of the video into these two regions. So let's just regress. Let's just compute a bunch of low-level features. Okay. From this video, what we're going to do is we're going to extract a bunch of low-level features from each of these regions. And we're just going to build a regression function that will tell us what the count is from those features. Okay? What are these features? Very simple features. Some of them have to do with this area, so the perimeter, the amount of bumpiness in these regions, and so forth. Others are things like texture features and edginess features extracted from the interior of these segments. So they're simple, classical textbook type of features. And so all that this system does is, we have the video, we run it through our model, we segment the video into different different flows, and then for each flow we have a regression function that maps those features into an estimate of the number of people.
How do you get FR and FL?
Sorry?
How do you get FR and FL?
So those are learned. So I have this is just a Gaussian process regression. I have some examples, and I trained the regression system, and then I learned that regression model. Okay. So why should this work? Well, obviously the properties of these regions are going to be proportional to the number of people that are inside these areas. Okay. And in fact, in a perfect world or whatever, you should be able to do a lot just by looking at the size of these regions. Okay, and that's what's shown here. So this is the plot of the segmentation area versus the number of people in the scene. And you see that there's a strong correlation between the two. And then there's a lot of local non-linearities that have to do with the fact that people occlude each other. Sometimes they walk together more closely, other times they don't. And that's really why the reason why we use all these other features. We use things like edges and texture and so forth, and we extract a 30-dimensional feature vector from each of these segments, and then we just run it through a Gaussian process regressor, which is if you don't know what it is, it's sort of a standard statistical tool to regress variables. So given x, you want to predict what y is, and that's what a regression function does. This allows us to have sort of sophisticated non-linear model, non-linear behavior.
So for the training, you do count the number of people for
yes.
each area, and then you
right.
have this regression function.
Exactly.
Okay.
So we do count the number of people, and then we train the system on that. Okay. So this is the what. So let me stop this, and then I'll explain what's going on. Okay. So this is the video. Okay, here we have the estimate produced by the system. So the red, arrow corresponds to the people that are moving in that direction. So the ones that are assigned to the red blobs here in the segmentation, and the green arrow corresponds to the people that are coming. So this is the estimate of produced by the system. This is the ground truth. Because this is a Bayesian sort of method for estimation, we also get a standard deviation for the estimate produced by the system. Okay, so this is what it looks like. So you should probably look at those numbers. It's probably the easiest thing to do. As you can see, it's kind of a complicated scene. There's sometimes people are going in front of each other. They occlude each other. Whatever people are doing in this scene. Okay. And so, one of the nice properties here is that it's very robust. Again, if you go into my website, you know, there's like hours of this stuff in there. So this is literally the training set that we use. The thing that it's on the same scene. It's not like, you know, yeah, I mean, it's, like I said, I mean, you know, this is literally the training set that was used. And then, you know, there's like, you know, hours of what's going on.
So no, if the problem was to find out, so to find out people walking individually, people walking in a group, would this method be enough, or do I need something? Because you are segmenting out people walking in a group and people walking individually.
Sure.
So would this be enough for you to recognize those kinds of activities, or do I need trajectory level analysis for that?
I don't think you do. I mean, I'm not claiming that this particular thing we did would be enough, but you could build models like this that you could learn what those things look like. And you know, I'll talk about anomaly detection too, and you know, and I'll show some results on that too. And those are very individual thing. I'm not saying that, you know, this particular thing that we did, which is geared for like counting the number of people, that is the solution to all, you know, the problem. But I do think that I question the assertion that you would need to do tracking even for that. Now, if you want to track a specific person or something like that, then that's a different issue. But I do think that it will be possible to extract with models like this, you know, behaviors that are actually, you know, sort of subtle, and that really, because I could classify like each, you know, what's going on in each of these regions. I could build a classifier just for that, and you know, and if this is able to tell me how many people are there, there's no reason why it shouldn't be able to do that as well.
You can learn the behavior within each segment.
Right, or you can, and yeah, I mean, like I said, let me keep going because, you know. Okay, so this is a comparison that we did, like in one of our papers, where we actually compare this to sort of a pedestrian detector. Okay, you know, what would be, you know, how could we solve this by just using like you know, a standard pedestrian detector from the literature. And so, you know, we just got those, you know, we sort of ran them through this data. If you don't do any post-processing, it's like, it doesn't work at all, as you can see here. So without like some sort of temporal integration or whatever to get rid of all the false positives and stuff like that, it makes lots of errors. So, you know, we actually put some effort into sort of getting rid of these things and you know, and trying to do like you know, trying to get it to work. You know, what you can see here, so these are the results for the, you know, 3 different methods. These are 2 pedestrian detectors. So, you know, the error, we can never get the error to be, you know, as small as we can, as we have for this Gaussian process-based solution. Okay, so the error is like 1.79 people. For these guys, we could have like 4 or 5. So here it shows you a little bit why. So these are the curves of the counts in blue, and the ground truth is shown in black. Okay, you know, by looking at the video, the things where the pedestrian detector struggles on are the standard ones. You know, when there's a lot of occlusion, or where people are really close by, you know, as the number of people starts to increase, you know, as the scene gets more packed, it starts to have, you know, it's really hard to detect these pedestrians because there's not a lot of, sometimes that you can see. You know, this thing just does a much better job of sort of following the ground, as you can see here. So that's, you know, an example of, you know, the things that I was talking about. So this is like, this is like a plot over an hour, okay, of video. Like I said, you know, you know, this thing can run for hours. Here are, you know, examples of different types of scenes. You know, these are totally sort of unscripted. Sometimes, you know, the errors that it makes are because, you know, like at ECSD they have this sort of carts that drive around with food and stuff like that. So, you know, a lot of the errors are because of, you know, those types of objects. But, you know, it can go from sort of, you know, scenes where there's not a lot of people, all the way to scenes where there's like, I don't know, 50 people or whatever the numbers are. But, you know, really sort of, as, again, we don't have control over this environment, so, you know, whatever the crowd numbers were, you know, let's say peak hours between classes or something like that. Okay, so that's crowd counting. And, I mean, going back to, you know, what I said initially, one of the points here is that this is not that hard to do. I mean, it's not, this isn't a system that requires a lot of tweaking. It doesn't have a lot of free parameters. It's a fairly simple sort of combination of EM with a regression function. Okay, and so you know, a system like this, I think, could be useful for, you know, just like a low complexity sort of thing for crowd counting, which, like I said, it's a hard problem. We've also started looking at, okay, so now we have these models of this crowd behavior. Can we use that to detect sort of anomalies, you know, things that are unexpected, okay? And we've been doing some of that work. How am I going on time? I should be done? Okay, well, okay, so, I mean, I can just, how much longer do you want me to go?
5 minutes.
Okay, all right. So, so I'm not going to go over this into a lot of detail. So basically the idea is, once you have these models, then you sort of have a model for like standard, you know, crowd behavior, and one can think about sort of anomalies and detecting anomalies. So we've built together, let me just skip to the part where I talk a little bit about this. So we've built a model for anomaly detection that has, you know, two components. They're sort of a temporal component, so detecting things that are anomalous because they're different from the things that you've seen in the past. And that's what we refer to as anomaly detection. And the idea is, you know, we just break the visual field into a number of areas, and so we learn one of these models for each of these areas, and we find things that have low probability under that model as anomalous. The other part of anomaly detection is sort of like something is anomalous, somebody is doing something anomalous because it's different from what the other people in the scene are doing. So it's like, you know, it's anomalous because it's unlike what everybody else is doing. You know, it might be that walking in that area is normal, but today nobody's doing it, so, you know, when maybe that's because you can't or whatever. And so there's this notion that you can't just look at things that are sort of you haven't seen before, but also things that differ from like what the other people in the crowd are doing. And we've, you know, built some, we've been studying saliency, which is sort of how this type of anomaly detection is done in the visual system. And we have some models of saliency, and we've, you know, including them here. So I'm not going to go into details because I don't have much time. But it turns out that you can combine those sort of dynamic texture models with models of saliency, and then find, you know, anomalies like spatial. Okay, let me skip this. Okay, so here's like some example of what we're talking about. So we have some, you know, center surround sort of saliency operator that combines center surround and these, you know, the mixtures of dynamic textures, and then we can find things that are very different, that are behaving differently from the other people, from what the other people are doing in the scene. Okay, so the anomaly map is a combination of those two, and let me just show you some results. So there's a data set that we put together. If you guys are interested in, you know, looking at this. So it turns out that one of the hard problems in anomaly detection is actually defining what an anomaly is. So we define